Hi everyone. So this is just an optional extra video for people to watch if you're interested. Basically, this is a topic that I generally don't have time to get to when we do in-person classes, just because there's so much other material that we have to cover in this class. But I figured since we're online, I might as well make a video that you can watch if you're interested, or you can skip if you have too much on your plate. So basically what this video is going to be focusing on is functions, rational functions that do not have a horizontal asymptote. We'll see that there is a way to predict what the shape of their end behavior is going to look like, and that they actually do have asymptotes even if they're not horizontal asymptotes. So let me kind of summarize what I just said and rephrase it a little bit. So a function has a horizontal asymptote. Basically, if its graph, or I'll just say if it eventually approaches a horizontal line. So what I mean by that is, if you think about what it looks like when a function has a horizontal asymptote, the graph is getting closer and closer to being horizontal. So it's getting closer and closer to that horizontal line that would be the horizontal asymptote. So what we'll see is that rational functions that do not have horizontal asymptotes basically they will instead eventually approach a different graph shape. So when I say different, I mean different from a horizontal line. So we'll see that, that rational functions, instead of leveling out to a line, well, here's a couple of examples of what they could do. So this one, the one in red, f of x is equal to 2x cubed minus 9x squared plus 13x minus 1 over x squared minus 3x plus 2. So this function does not have a horizontal asymptote, right? When we talked about how to find horizontal asymptotes in the previous video, we talked about degree, right? We talked about how if the degree of the numerator is bigger than the denominator, there will be no horizontal asymptote. So what we're seeing instead is that, so the thing that's graphed in red is the actual function. This black dotted line is not part of the function. So what this actually is, this black dotted line, this is an asymptote. So this has what I would call a linear, and then sometimes, and I think your book probably does this, frequently this will be called a slant asymptote. So why do I say it has a linear asymptote? Well, if you look at what is the shape that this graph is eventually taking on, I know it might be a little hard to see in this picture, so don't worry, later I'll show you this graph on Desmos and we can like zoom in and actually get a better idea of what's going on. But notice that the red graph is getting closer and closer to like matching this diagonal line. And so it has this asymptote that is not a horizontal line, but instead just a linear function, some other line. Now this one, and I don't, for some reason the color changed. Let me make that back to green. So this function, again, if you were to just go by the rules of our last video, you would look at the degrees and you would say, well, the degree of the numerator is bigger than the denominator, so we don't have a horizontal asymptote. And that's true. There is no horizontal asymptote in this graph. However, if you look at what kind of shape the graph is taking on when as x gets larger and larger or smaller and smaller, it's actually approaching the shape of a parabola. So this has a parabolic asymptote. And you can have, basically, you can have any kind of polynomial function as your asymptote. So you could have an asymptote that is a cubic function, a degree 4 function, a degree 5 function, and so on. In this video, we're just going to focus on these two examples. but just know that you can have all sorts of different types of graph shapes as your asymptote. Okay, so the question that we're going to be focusing on in this video is, how can you figure out what type of asymptote a rational function has? So we can kind of answer that question already. So one thing that you might have noticed, what's the difference between the numerator and denominator in these two functions? So you might notice that in the function on the left, the numerator is only 1 degree higher than the denominator, right? It's 3 and 2. And so if you think about what does a degree 1 polynomial look like, it's a line, right? And so the asymptote ends up being a line. Whereas this one, the one on the right, now the difference in the degrees, this one is degree 1, so the difference in the degrees is 2. And what does a degree 2 polynomial look like? It's a parabola. So that's kind of one way you can figure out, like, generally speaking, what shape the function will generally resemble is look at the difference in the degrees. However, we can do even better. So what we're going to figure out in this video is not only how to recognize, oh, this is a diagonal line, or oh, this is a parabola, but like to find the specific equation of the line or the parabola. So what we're going to do in this video is we're going to use polynomial long division to rewrite a rational function in the form f of x is equal to q of x plus r of x over d of x. And that's kind of a complicated expression. Let me explain what I mean by each of these pieces, and then I think it will become even clearer when we do an example. So q of x, this is not, so you might remember in yesterday's, or in the previous video, we were talking about like p of x over q of x, and q of x was the denominator. This is a completely different usage of q. Don't associate those two uses of the letter q. It's completely different. So here, q stands for quotient. So the quotient is basically the answer. Like if you're doing long division, the number that you get as your answer is called the quotient. This r of x, this is your remainder. And then d is your divisor, so the polynomial that you're dividing by. So we'll see how that plays out in an example in a second. Okay, so let's start with the first function that we looked at. So this was the one that was graphed in red. We should see that this has a linear asymptote. Okay, so we're going to start by just performing polynomial long division. So we're going to take the function on the top and we're going to divide it by this function x squared minus 3x plus 2. Okay, so first thing we're going to do is divide x squared into 2x cubed, and so our answer is 2x. And so then we multiply 2x with this whole function on the left, right? That's how polynomial long division works. So we get 2x cubed. Then we get minus 6x squared. Sorry. And then we get plus 4x. And so now we need to take this whole thing and subtract it. So this becomes minus, this becomes plus, this becomes minus. And so we end up with 0, and then this is negative 3x squared, and then this is 9 plus 9x. And then we bring down the minus 1. Okay, so our next step is to divide our divisor. So the x squared minus 3x plus 2, now we're going to divide that into negative 3x squared plus 9x minus 1. And so how many times does x squared go into negative 3x squared? Well, negative 3. And so now we take negative 3 and multiply it by what's on the left, and so we get negative 3x squared plus 9x, and then minus 6. And so now we subtract everything. So this becomes plus, this becomes minus, this becomes plus. And so the first two terms both cancel out, right? We get 0 plus 0, and then here this becomes -1 plus 6, so that is plus 5. And so we don't really need all this stuff. Really, all we need to know is that our remainder is 5. And so what this tells us is that our original function f of x, instead of writing it the way that it was originally written, it can also be written as our quotient, so our answer, and our answer was 2x minus 3, plus our remainder, so our remainder is 5, and then the denominator is the thing we were dividing by, right? So we have 5 over x squared, minus 3x plus 2. Okay. So when we're looking at this new form, so I just want to be really clear that if you were to go into Desmos and if you were to start by graphing this, so if you type this whole function in, and then you went and you typed this function in, they're the same exact function. So all we did, it's kind of like completing the square. We went through a procedure to find a different way of writing the same function. So how can we use this to figure out what the kind of asymptote we're going to have? Well, it turns out that this function right here, this is going to be our asymptote. So our asymptote is going to be y is equal to 2x minus 3. And I'll show you that in the graph in a second. But first I want to explain why. Like, is it magic? Like, why does that end up being the asymptote? Well, let's think about what happens to this expression. So this whole thing down here, when x is really large. So when x is really large, and specifically let's focus on this. What happens to this expression when x is really large? So when x is really large, this will be 5 over some huge number, right? Like 5 over a million or 5 over a billion or something like that. And so what kind of a fraction is that when you have 5 divided by some huge number? That becomes really, really close to 0. Right? So this part, as x approaches infinity or negative infinity, I'll say it this way, I'll just say plus or minus because it happens in both directions. This expression, so 5 over x squared minus 3x plus 2 is going to get closer and closer to 0. And if you don't quite get that, I would encourage you to try some examples. So try plugging in like 10 for x and then try plugging in 100 and 1,000, and you'll see that the bigger the number you plug in for x, the closer and closer this part is going to be to 0. So what does that tell us? Well, that tells us that if we plug in a really big number to this function, so when x is very large or very small, our function is basically going to be approximately equal to 2x minus 3, right? Because the part that is circled in green is going to be really close to 0. And so the bigger the value we plug in for x, the more and more the part circled in blue is really going to be like the kind of dominant portion of this function, right? Because the green part is going to be getting tinier and tinier. And so what we're going to be left with is something that really closely resembles 2x minus 3. And so the function is going to be approximately equal to 2x minus 3, and that's exactly what we'll see in the graph. So that is the second one. Let me pull up the first one. So here's our rational function that we saw earlier. And then here I have graphed y is equal to 2x minus 3. And so what we can see is that if you plug in bigger and bigger values for x, I mean, already it almost looks like it's overlapping, but if you zoom in far enough, you'll see it's not exactly overlapping. It's just getting closer and closer. So the red graph is getting closer and closer to approaching the line 2x minus 3, and then same thing happens in this direction. Okay, so let's do the same thing to figure out what the quadratic or the parabolic asymptote was in this example. So in this example, we want to do negative x cubed plus 4x squared minus x minus 7 And we're going to take that and divide it now by x plus 1. Okay, so x goes into negative x cubed, negative x squared times, and then we multiply and we get negative x cubed minus x squared. And then we subtract, so these both become plus. And so we end up with 5x squared minus x minus 7. And so now we divide x into 5x squared, and so that's going to be 5x. And we multiply and we get 5x squared plus 5x. Then we subtract, so these both become minus, and so we now have 6x, or negative 6x, sorry, minus 7. Now we divide x into negative 6x, and that is negative 6. Then we multiply negative 6, and we get negative 6x minus 6. We subtract this, so these both become positive. And so we're left with negative 7 plus 6 is negative 1. And so what this tells us is that our function can be rewritten as f of x is equal to the answer, which was negative x squared plus 5x minus 6, plus our remainder, which was negative 1. So that means that we could also just write this as minus 1 over our denominator. So our denominator was x plus 1. So same thing happens as before, right? So if you think about what happens as x gets larger and larger, so or smaller and smaller, so as x approaches either positive or negative infinity, what's going to happen to this expression, negative 1 over x plus 1? Well, that's going to get closer and closer to 0, right? If you plug in like 100, you'd have negative 1 over 101, which is a very, very tiny fraction, very close to 0. And so what you're going to be left with is that this function, when x is very large, or very small, your function is actually just going to be approximately equal to negative x squared plus 5x minus 6. And so what this tells us is that this part right here, this is the asymptote. So we'll see that the parabola that our function approaches is the parabola y is equal to negative x squared plus 5x minus 6. So let's take a look at that. Sorry. There we go. So here is that function. And I'm going to now put the parabola. So the black dotted line is the parabola. Y is equal to x squared plus 5, or negative x squared plus 5x minus 6. And so we can see that as x gets larger and larger, so as we move to the right, the function is getting closer and closer to this black dotted line to the point where it almost looks like they're overlapping. Although, like on the last one, if you zoom in enough, you'll see they're not quite overlapping, but they're almost there. And then the same thing happens in the negative direction as well. So the last thing I just want to show you is that this same kind of approach actually also works with horizontal asymptotes. So you could actually do the exact same thing for an example like this and also see that you have a horizontal asymptote. So how would you go about doing this one? Well, you could still do division. So even when the degree is the same, you can do long division. In this case, you would need to put in a kind of space holder, right, for the 0x because there is no x term. Just make sure that things line up correctly. And then we're dividing by x squared minus 5x plus 6. So this time we're dividing x squared into 2x squared and we get 2. Then we multiply and we get 2x squared minus 10x plus 12. And so if we subtract these, this is minus, this is plus, this is minus. And so we end up with 10x, what is this, minus 13. And now we can't do any more, right? We can't divide x squared into 10x minus 13. So what this tells us is that our original function, what was I calling it, h of x, can be written as our answer, which was 2, plus our remainder, which was 10x minus 13, over the denominator, which was x squared minus 5x plus 6. So this one is not quite as easy to see as in the last two examples, but it will still be true for this expression that as x approaches plus or minus infinity, this expression, 10x minus 13 over x squared minus 5x plus 6, that is still going to head towards 0, right? Because even though this time the numerator does have an x in it, well, the denominator has x squared. So the denominator is going to get bigger and bigger compared to the numerator, and eventually this expression will get towards 0. And so what this tells us is that when x is very large or very small, that the function h of x is basically just equal to 2, right? It's equal to 2 plus this other thing that is getting closer and closer to 0. And so just to remind you, we actually did this function in a different video, but here is the function that we were just talking about. Sorry, I'm at the bottom half of it, got to go up here. And we can see that it eventually approaches y is equal to 2. So it's not like the stuff we talked about in this video is only applicable for kind of funky types of asymptotes. It's true for all asymptotes. It's just that there's a much easier way to do it for horizontal asymptotes, right? You can just look at the leading coefficients. But if you really wanted to, you could still do long division to find the horizontal asymptotes. Maybe I'll just add that quick note here that this is the asymptote, right? So this is telling us that the asymptote is going to be y is equal to 2. All right, so that is it for this video. Hopefully you found this kind of interesting. I didn't make a worksheet to go along with this just because it is kind of a bonus thing, but yeah, definitely feel free to play around with some of the, we've seen actually a good number of examples in the last video that did not have horizontal asymptotes, so you could play around with those and see what you get when you do the long division and compare those graphs, and you can verify that you actually have the asymptote that you got from your long division. All right, see you all in the next video.